back to a lecture series on hydrogeology. So in this lecture, we are now going to discuss about the the groundwater exploration methods. There are many methods are available for assessing the groundwater or understanding where exactly the groundwater is there in the subsurface. Because once if we done the assessment, then we'll be able to dig a well, and then the expected water will be taken out. So groundwater exploration is the hard part of any hydrogeological studies. In this lecture now we are going to discuss about the groundwater exploration methods, especially the surface methods, how the surface methods are likely to be investigated. The groundwater exploration, it is nothing but the investigation of groundwater formation. It is underground formation, and we are going to investigate the underground formation to understand the movement of water in three forms as hydrological cycle. The liquid which falls immediately after the rain goes down, percolate down to the ground, and then reaches the surface of water table. So we will have to assess at what depth exactly the water is there. Once if we assess, then we have to use the groundwater quality and to identify the nature, number and types of aquifers. Different methods, as I said. The first method is surface exploration method. In this method, there are two parts. One is lithological interpretation, second one is structural interpretation. The second one is subsurface exploration by geophysical method, and third one is by using satellite technology or the aerial photograph to investigate the possibilities of groundwater. The flowchart shown here, surface explorations are of geological methods, lithology and structure. Geomorphological methods, understanding the various landforms and its influence on groundwater resources. And then third one is hydrogeological studies by integrating lithology, structure and geomorphology. And subsurface, surface geophysical methods. There are plenty of methods available, of which the well-known method or universally accepted method for assessing the groundwater is electrical resistivity method. So in this method, we'll be able to assess the subsurface variation at exactly which location, how many aquifer types are there in the subsurface. And the seismic refraction, it's not of much use, but this is being used for earthquake studies. Seismic refraction and reflection, gravity, magnetic, and GPR. Now GPR has got a lot of applications in all the fields like minerals and water. Of course, electrical resistivity method and GPR is highly nowadays used to interpret the depth of water table for the groundwater exploration. Coming to the surface methods of geological investigation, now let us see. It is very important, of course, understanding of the rock, understanding of the mineral characteristics, understanding of the mineral assemblages, understanding of the different structure involved in the particular area. Only the geological studies are highly useful. Hence, the importance are increasing only, and the geoscientist people to be able to assess exactly at what depth water will be there. So in a first step as a geologist, we will have to start investigating. Rather, we can say it is a refinement study. We will have to do it while suppose when you are going to do any assessment, refinement study is the preliminary investigation, is the first one to do it. In the first one, what we are now going to do to assess where the surface water is there, what type of occurrences will be there in that particular area, what is the lithology. As we know, there are three methods and three lithology. That's what we are now going to discuss in detail about the subsequent sections, like igneous, how it behave, metamorphic rocks, how it will behave for groundwater conditions, and similarly for the sedimentary rock. The type and terrain, the type and terrain or the rock formations, type and terrain of the rock formations, lithological units, geological structures like lineament, fold, fault, joint, and fracture system. So the type of terrain, what type of rock it is, what is the lithological unit it is, and geological structures, very important structures like lineament, fault, fracture, joint, fold. So this is acting as a conduit zone through which the water will move down to the surface to reach the water table. These long linear natural features and folded structures, faulted structures, and joints, wherever the joints of two different rock formations are two different mineral groups. So there through which the joint, through the joint the water will penetrate down to the ground and fractures, cracks, has got a lot of applications with respect to the groundwater movement in the subsurface. Only after geological investigation, the type of geophysical method to be conducted. Only after this, we can suggest at what the probable depth may be 500, 600, 700, or sometimes 2000 feet below the ground. Again, now we will have to fix what type of it is. Aqueous system in fractured rock formation is given. You see, it is a granitic boulders, and then this is the fractured rock. You can find number of fractures in between. This is the fault, the movement, the displacement of rock, and you have a aquifer system here and the fresh basement. When the water conduits through the fractures and it reaches the water table is static. It is uniform throughout the area, and water conduits down to the surface, over which on the surface you have your sediments. And this is the another one where you have weathered zone. Of course, normally you have the formations like topsoil, weathered zone, depth to basement. So in the topsoil, the loose sediments are there on the top of it, and below which, that over the period, because of the rain, either physical activity or by chemical interactions, what will happen, after the subsurface soil, the rocks are degraded. So that is called weathered zone. If weathered zone thickness are more, expected possible movement of groundwater more in that particular area leads to higher groundwater potential. So this is how the system is there in the subsurface. So it is a cross section of the subsurface in the lithological unit. So under geological methods, geology of the area has to be studied. Now you will have to assess what is the thickness of soil, what is the thickness of alluvium cover, what is the thickness of weathering, whether it is a jointed area or fractured area or shear zone area, and what is the porosity, that what we have studied, porosity and permeability. Is it porous rocks? If it is porous rocks, in turn we'll be able to expect more groundwater, indicate good storage. So all these things we will have to assess. So once if you get anything of this, then we'll be able to get the possibilities of more groundwater. Whereas massive igneous and metamorphic rocks or impermeable shales indicate less groundwater potential, paucity of groundwater in that particular area. It means movement is arrested. If there is a massive igneous rock, there will not be of much movement. If there is impermeable shale, also will not allow the water down to, so wherein you'll be able to get only less amount of groundwater potential. Similarly, porosity and permeability. So this is the main parameter of any groundwater system to be understand. If it is high porous and high permeable zones of dense rock, encourage storage of groundwater. Massive rocks do not permit the water to sink. Joints and faults in the rock, water sunk into the ground, into rocks with interconnected joints, fractures, fissures, and crack, which will yield a good amount of groundwater in that particular area. Proximity, distance from the river, distance from the streams will also have influence. If you have a river system, definitely the adjoining areas are enriched with water, because of the water over the period of time, the water will move in a river or a stream. So slowly it percolates and then moving into the subsurface groundwater system. In turn, wherever the river is there, it is, obviously we will be able to get more groundwater. So this is one best examples of how cracks are formed in the rock, and this is one best examples of joints. It's a long linear natural features. If it is so long in kilometer, that is called lineament, and through which also the water will move down to the surface. And you can find the weathering. So this is the weathered zone. Weathered zone will have, again, the open spaces or the interconnected open spaces are more in this, and similarly for the fissures, it is also moving down to the surface. So the first part of the discussion, geology. So in the geology, now we are going to discuss about how lithology is controlled. There are three rock types, as we know. One is igneous. Igneous, if you take igneous rocks, it is weathered rocks which normally have, in the last slide I have shown, higher porosity and higher permeability. Definitely it will act as a good aquifer. In ultra basic rocks versus acid rocks, ultra basics are good when compared to what is that, acid rocks. Acid rocks doesn't have much porosity, or doesn't have, if porosity is not there, then there is no question of permeability also. Similarly, coarse texture rock showing higher yield than fine texture. Yes, if it is coarse texture, if it is fine texture, what will happen? The packing will be more, so that the quantity of porosity will be reduced, and in turn permeability also. That's why coarse specimens or the coarse textures rock will have higher expectations of groundwater than the fine grained sediments. Examples are pegmatite, which is good, granite and charnockite, which is less. Similarly, volcanic rocks are good groundwater potential than deep plutonic rock. Volcanic rock are exposed on the surface, leads expected weathering and what is that? Weathering conditions are more in the volcanic rock, whereas it is not possible in the deep-seated plutonic rocks. Similarly, for basaltic rocks are good due to their columnar joints. Basalts, which are normally there, it has because of the columnar joints, it will act as conduit zone through which the water will move down to the surface. Coming down to the sedimentary rock, how the lithology is controlled for the groundwater exploration. There are many rock types, of which the major which controls the groundwater is clay, sandstone, and limestone. Clay, sandstone, and limestone. Clay shales are good groundwater tapping rocks, high porosity and low permeability. Because of the high porosity and low permeability, water stays in this particular rock for over a period of time. That's why that it is good for agriculture purpose, because agriculture, we are in need of water for quite a long time. Once if you pass the water, you are expected your agriculture ground should have the capacity to hold water for some time, at least 3-4 days by the time the plant will grow. That's why clay and shales are good for groundwater tapping rocks. Lack of horizontal permeability in these rocks is the major reason for holding the water for some time, and then it is not allowing the water to move either on the parallel or on the subsurface. And coming down to the second major distribution of sedimentary rocks is your sandstone. Normally, sandstones are good aquifers. Best examples of water-bearing rock is sandstone. But here also an issue considered like grain size and shape control the groundwater. If coarse-grained rock, good groundwater. If it is fine-grained sandstone, that is that the groundwater potential is it is reverse. It is said to be low. And shape, if the round shape is there, it is expected good groundwater potential. And similarly, sharp and angular, if rounded shape, it is okay. If sharp and angular, it is comparatively less in when compared to the round grain of sandstone particles. Similarly, for the sorting, well sorted is expected to have good groundwater potential, and poorly sorted, it is with low groundwater potential. Similarly, for limestone and dolomite, unweathered is less groundwater, and weathered limestone, you'll be getting, what will happen. See, calcium carbonate will react with H2O, then you'll be able to get sinkholes therein. So if the sinkholes comes, then there is a good movement of water in the subsurface in a limestone area, wherein the interaction leads to the growth of limestones on the top and from the bottom, called as stalactite and stalagmite. There the groundwater potential is high if provided good amount of surface water exists. Coming to the metamorphic rock, how lithologically metamorphic rock controls the groundwater potential zones. Metamorphic rocks are a moderate groundwater potential zone. High metamorphic rocks are good groundwater potential zone. Cysts and gneisses are good groundwater zone, and quartzites and marbles, because of higher fractures in joint fractures, water will not stay over the period of time here. It will, in no second, the water movement will be more in this area. That's why, in turn, the movement is high and the potential is less. So this is how the lithology is controlled. Lithological characteristics has to be studied for groundwater exploration in the first step. So with this, the discussion of groundwater exploration of surface methods like geology method, lithological control is come to an end. Thank you very much.